All right, welcome to this explainer. Today, we're diving straight into a massive, honestly game-changing breakthrough for enterprise AI. We're looking at exactly how complex AI systems can achieve completely predictable execution right now today. And the best part? We're talking about doing this without retraining the model and without throwing massive amounts of new compute at the problem. If you follow AI architecture, you know this is basically the holy grail. So let's break down exactly how it's actually being done.
Here is our roadmap for today's explainer. We'll start with the predictability gap, define attractor engineering, walk through the three-mode experiment, test stability under perturbation, look at measuring path emergence, and wrap up with engineering emergence today. Let's jump right in. Section 1, the predictability gap. Why enterprise AI desperately needs execution over just peak intelligence. So, here's the million-dollar question for this explainer. A highly specific, highly testable one. Can structure alone stabilize reasoning when a model's weights and compute remain completely fixed? Think about that for a second. We aren't changing the brain of the model at all. We're asking if the right structural framework can pull chaotic, wandering outputs into a reliable, stable orbit, what we call an attractor. To really understand why this matters, you have to look at the difference between peak intelligence and predictable execution. Standard models are absolutely obsessed with chasing peak intelligence, getting smarter, absorbing more and more representational data. And hey, that's great, but it's also highly unpredictable. Enterprise AI doesn't just need a model to blindly pursue unpredictable peak intelligence. It needs predictable execution. It needs the traversal path, the actual step-by-step journey the AI takes to get to an answer, to be stable and fully reproducible every single time. Moving on to Section 2, Attractor Engineering Explained. Let's look at the energetic paradigm mechanism.
Okay, this brings us to Inference-Level Attractor Engineering. It sounds super dense, but here's what it actually means in practice. We are using strict structural constraints to guide a fixed model into a stable reasoning basin. Basically, you're setting up guardrails that mathematically force the model to stay on its path. Think of it like putting up bumpers in a bowling alley for your AI's logic. And the kicker? It requires zero retraining, zero additional compute. You are literally engineering the environment around the inference, rather than rebuilding the model itself.
Now, I want to be crystal clear here. We are not talking about some speculative, maybe someday future possibilities. The energetic paradigm, or EP, achieves the structural transition today. We're not sitting around waiting for the next massive trillion-parameter model to hopefully fix these stability issues. The structural transition at this level of analysis is already an achieved reality.
All right, Section 3, the three-mode experiment. It's time to put this structural scaffold to the test.
To prove this works, let's look at a strict laboratory experiment comparing three very different operational modes on the exact same task. First up, Mode A. This is unconstrained free generation. The model just plans however it wants, total Wild West. Then we have Mode B, where we apply a mild constraint by lowering the temperature to reduce randomness, but it still has no formal structure. And finally, Mode C, where we enforce a strict structural scaffold on the entire reasoning process.
In Mode C, this specific scaffold forces the model through a relentless strict loop. There's no skipping to the end here. It literally has to define the state, identify the constraints, generate its subgoals, evaluate those recursively, and only then is it allowed to conclude. It's totally locked into this logical pathway.
Which brings us to Section 4, Stability Under Perturbation, aka the stress test.
Let's be real. Anybody can get an AI to follow instructions in a perfectly sterile environment, but enterprise data is messy. So for this experiment, we actively disturb the task. We inject completely irrelevant noise and sentences. We mess with the word order. We mask non-critical info, and we paraphrase the core instructions. The whole goal here is to try and break the model's reasoning path to see if it spirals out of control under pressure.
Section 5, Measuring Path Emergence. The metrics of stabilization.
We can't just go off vibes here, right? We need hard, data-driven numbers to measure the results of all this chaotic disturbance. So we meticulously track three things. First, trajectory similarity, meaning do the intermediate reasoning steps still converge even when the input is totally scrambled? Second, convergence speed. How fast does the structure actually stabilize the model? And third, error type stability. If the model does fail, do the errors shift from being totally chaotic and random to being highly predictable and manageable?
The data reveals a night and day difference, folks.
While Mode A and Mode B completely drift into chaos under perturbation, they solve the problem differently every single time you scramble the words, the structurally constrained Mode C maintains incredibly tight, predictable trajectory similarity. The scaffold acts like a gravitational pull, keeping the model's logic right on track despite all the noise.
As this visual confirms, inference-level attractor stabilization is achieved. Multiple chaotic, wandering reasoning paths successfully collapse into one stable basin. This proves, without a doubt, that an AI attractor has been successfully induced entirely by structural conditions.
So here's the absolutely crucial takeaway. The value here is not that the model becomes smarter. It didn't suddenly learn new facts or get a boost in representational intelligence. The value is that its reasoning path, the journey it takes from input to output, became infinitely more stable, reproducible, and resistant to perturbation. That is, inference-level emergence as path stabilization. Finally, Section 6, Engineering Emergence Today. Let's talk about the reality of EP. Now, let's set a clear guardrail. We aren't overstating things and claiming EP magically solves every single frontier-scale AI problem in existence, but we are proving that it demonstratively and experimentally achieves this specific structural mechanism, attractor engineering, today at the levels covered by this analysis. What this means for you is that we possess the exact structural conditions required to make AI path stabilization achievable, completely stable under stress and deeply testable, right at the inference layer. You don't need a multi-million-dollar training run to fix your model's wandering logic. You just need structural discipline.
And this brings us to the absolute core finding, the mantra of this entire explainer. Bigger models wait for emergence. They just keep adding parameters, crossing their fingers, hoping stability eventually appears. But EP already engineers it. By changing coherence, path discipline, and attractor formation, the stability is engineered by design from day one.
Which leaves us with this final thought for your own enterprise architecture. Look at the systems you are building right now. Are you simply waiting around for unpredictable peak intelligence to hopefully emerge in the next massive model update? Or are you ready to engineer a stable, predictable execution path today? The tools for attractor stabilization are already here. It's time to start building with them. Thanks so much for joining me on this explainer, and I'll catch you on the next deep dive.